Well, good evening, everybody, or evening for me, afternoon for those in Western Canada, and good morning to those of you in Australia. It gives me great pleasure to bring this week's seminar, Jim Macnae. I'll tell you a little bit about Jim in a minute. But before we go on to Jim, just a quick note about what we have coming as we roll out the EMinar series next week. Is Juan Carlos Afonso, who's going to talk about multi-data, multi-scale probabilistic inversion. And then we have Alessandro Santillano, who will also talk about a probabilistic method, swarm intelligence. That'll be followed by Phil Wanamaker on petrological systematics. And then we have more Australians, Kate Selway and Sinan Azadin on their code MATE, which is where they put laboratory results into code. And Yasuo Ogawa is the penultimate presenter who will talk about fluids in the crust, seismological and volcanological applications. And then finally, to end season one, we have Lucy McGregor, who's the SEG Q1, Q2 distinguished lecturer, who will talk about multiphysics analysis. So today we have Jim Macnae, and it really does give me a lot of pleasure to have Jim speak to us. I've known Jim, believe it or not, 39 and a bit years when I started a postdoc at University of Toronto when he was finishing his PhD with Gordon West. And I know Jim to be an absolutely excellent scientist, very innovative. As his CV says, he grew up in South Africa. Did 3 years as a field geophysicist with geoterics, moved to Canada, did his master's and PhD at U of T with Gordon West. And he has many publications on EM, and you'll see his Physics of EM, an absolutely standard paper that everyone has to read, really. Time domain EM systems with Misak Nabigian in the SEG volumes. Loads of papers on ground, borehole, airborne EM, acquisition, modeling, interpretation, the whole bit. After 15 years in Canada, Jim moved to Australia, became professor at Macquarie and RMIT, developed commercial software, supervised numerous graduate students. A gold medalist of the ASCG, is now employed at CD3D and consulting to mineral exploration companies and contractors, as well as working on compact radio systems for deep penetration operation in space. Well, today we're going to hear from Jim on his latest work, so on UAVs. So please take over.
Okay, thanks. I trust my screen's visible and someone will jump up and down. Yeah. Okay. Okay, so I'd like to start off by thanking my research sponsors and employers for the last while, the last 30 years, some of which I'll be talking about today. So I'm starting off with an agenda of abbreviations, I guess. If everyone's used to being electromagnetics, I do a fair bit with Airborne EM. I'll be talking a bit about unmanned systems, then looking at some of the challenges of adding EM to UASs. I'll look at a project which investigated sort of Amazon-style delivery of EM ground stations. I'll talk briefly about EM on the moon. And finally, I'll talk about a new generation of sensors that's under development, which might change the way we can acquire data in years to come. Okay, so this picture just shows a few of the sort of common varieties of electromagnetic sources And receivers, you can have loops, grounded dipoles, antennas, lightning sources, power lines, the solar wind. So there's a big variety of possible choices for sources and sensors. Now, if we just look at EM as a wave, things started off with radio waves where you had low frequency, medium, and high frequencies. And things got extended as radios improved. They went to very high frequency, ultra high, super high, extremely high, tremendously high, and similar things down low. So each of these covers sort of a decade in frequency and a decade in sort of wave. So in terms of geophysical electromagnetics, ground penetrating radar works up in sort of the radar band, sort of the radio radar band. Magnetotellurics is tremendously low frequencies and lower. And the AMT audio frequency band covers everything from extremely low frequency up to probably VLF, very low frequencies. So most mineral exploration EM takes place in the quasi-static domain. And the quasi-static domain is where diffusion dominates, and we're not really dealing with wave-like behavior. So I'm going to be focusing in mostly on this band where wave physics is not really applicable. Okay, so I'm coming through another set of abbreviations. UAVs, which one of my female colleagues has informed me that they should be uncrewed aerial vehicles as opposed to unmanned, often called drones. I tend to use the term UAS, which is an unmanned aerial system, because that includes just the platform that flies, but it includes everything like the ground control, payload, communication. So there's a lot more in sort of a whole operating system than just a autonomous vehicle, semi-autonomous vehicle. MT, I assume this audience knows much better than I have. And just you might think it inconceivable that unmanned aircraft could have any use in sort of replacing buried 15 kilogram sensors and making measurements at 1,000 seconds. But we'll see by the end of the talk. AMT is sort of higher frequency variant, which is not used that much compared to controlled source, but nonetheless is seeing increasing noise. VLF, which from a radio communications perspective is a very low frequency. From a geophysical or quasi-static is actually a very high frequency, but VLF is something that's I'll be mentioning a bit. And AEM, sort of airborne EM. So just sort of a few terms that you're probably mostly familiar with. Okay, so last year, I was one of the scientists working on EMiR's P1204 project funded by the mineral industry and companies like Boeing and airborne contractors. And that project was developing UAV-mounted geophysical sensor arrays. So that's down at the bottom, there's a public report on that, which is anyone can download, and that provided a summary of geophysical state of the art. And I started off by looking at sort of the ground EM systems, many variations such as time domain, frequency domain, the different sources and sensors we've looked at otherwise. The systems operating in sort of over 11 decades of frequency, sort of bits of that as to which, and you get actually very different systems operating in different parts of the EM spectrum. There's a whole possible set of sources that people use in geophysical exploration: moving loops, fixed loops, natural sources, cultural sources, grounded injection current into the ground. Transmitters can be low power lightweight for shallow penetration, or high power heavyweight for deep and or distant operation. So there's multiple combinations. And the next sort of, I guess, obvious thing to look at in terms of unmanned aircraft is, what does airborne systems actually do at the moment? So that's part of the way to putting EM on a UAS. So existing systems, there's time and frequency domain systems. They are either wideband or a set of narrow bands, but there's no good systems that are operating much below about 25 hertz. So down the empty frequency band, there's no airborne systems that operate. There are some lower frequency systems operating in sort of trial mode, you might say, but they're definitely noisier than the higher frequency systems, and they're not yet sort of accepted as being an improvement or even a significant. There's a variety of transmitter sources used, similar to the ground systems. So the current airborne systems don't use the low power lightweight systems, other than in some unexploded ordnance applications where they've got very low flying helicopters. And part of the reason for that is the moment you have any aircraft altitude, it decreases your shallow resolution. So the low power systems are not commonly sort of airborne. So the ones that are common are relatively high power to get depth of penetration and to cover for the effects of altitude. And they're sort of heavyweight. So a system like Spectrum, which is shown here up at the sort of top right, actually uses a Lexus car engine as the power source to drive a generator inside the middle. So they're pretty decently sort of powered. They'll tend to use DPDT sensors. They won't measure electric fields, and they won't measure magnetic fields. So unlike sort of, say, MT, where you'll tend to use an induction magnetometer to measure B fields. However, even though DPDT sensors are used, often the integrated data is sold as a B field. Helps reduce dynamic range, but it's not a true B field measurement. And one of the big problems with existing systems is with the 25 hertz base frequency, they can't penetrate conductive cover in many parts of the world. And there are systems that also use natural sources, sort of FMAG type systems like ZTEM. Those tend to have relatively low spatial resolution. And the VLF submarine communication systems, those will tend to have limited depth penetration. Okay, so let's get on to unmanned aircraft. Why might they be attractive? Well, there's a batch of myths around saying that, well, they're safer than existing aircraft. You can use swarms of them because they're relatively inexpensive, they're efficient, they're pretty reliable, they're easy to operate. The reality is a bit different. They're not that safe. You can't fly them in regulated airspace due to danger to piloted aircraft. Obstacle avoidance is imperfect. swarms certainly fly, but there's huge charging transport size issues if you want to move a swarm around other than flying it. And in many countries, the existing regulations require one pilot per UAV. So if you're going to put out 100 UAVs, you're going to need 100 pilots. That's just not sort of realistic. Actually, because of limited flight times for the battery-powered ones, they're actually quite inefficient. And it takes a lot of personnel time changing batteries, supervising takeoffs, landings, etc. UASs are remarkably unreliable. The mean time between failures is 1 in 100 hours for the cheap UASs, about 1 in 1,000 for expensive ones. Whereas in commercial aviation, you're looking at 1 in 100,000 hours. So in actual fact, they're not inexpensive. The unreliability, you might lose, a $500 UAS, say big deal, but if it's got a 20K or a 50K instrument on board, that is a big deal. And that is what killed, for example, Fugro's Geo Ranger project, where they put magnetometers on unmanned aircraft, and they just kept crashing and became way too expensive. There's sort of a myth that UASs are pretty easy to operate. Well, most jurisdictions require trained and licensed UAV pilots for commercial operations, so it's not sort of that easy. And the other big issue is beyond line of sight, which is what you really need to be useful. It's heavily regulated and pilot intensive. Okay, so let's get on to some of the things where UASs are working and do work. The world's most powerful EM transmitters are the submarine communication VLF systems, and they have detectable signals thousands of kilometers away from the source, getting on to close to 10,000 kilometers. So currently, UAS do quite a decent job in collecting VLF data. There's quite a few separate commercial EM systems out there that'll collect VLF data for you. They'll tend to hang their receivers underneath the multicopter, so they need the tether because of significant EM noise. These things have got tons of communication noise and currents flowing around from batteries. There's pulse width modulated power supplies, all sorts of things. So you have to keep your sensors different. There are some systems, such as this one bottom right, where there's a transmitter one end, receiver at the other, with something like a meter and a half for separation. So sort of to replicate some slingram systems, those are sort of very sort of shallow. So those type of systems, which is taking a lightweight sensor and attaching it at a distance to a UAS work, it does okay. There's been quite a lot of research into other applications of UAS. I've just produced some pictures from a review paper by Wu et al. On SemiAirport EM Systems in China, where they use a large grounded wire for a high power transmitter, or they can use a loop. And they fly relatively lightweight sensors beneath a helicopter. They still need tethers. These systems have actually achieved quite low signal to noise. And putting out transmitters on the ground is actually inefficient compared to flying them. So these systems, to me, don't have an obvious sort of way forward to become really useful, but the Chinese certainly disagree. And there's a bunch of similar research gone on in Germany by Johannes Stoll et al., where they flew a system over a grounded wire source transmitter, and they could certainly measure the harmonics from the transmitter you see on the right, but that actually has pretty much inadequate signal to noise ratios for deep prospecting. So these systems have challenges, and at the moment are not getting good data at low frequencies. So P1204 asked the question, what can unmanned systems do that we couldn't do before? So we looked at what are the unsolved problems of existing systems. They can't get good data at low frequency, the airborne systems, because of rotation noise. I'll talk a bit more about that in a moment. That limits conductive cover penetration and our ability to detect very valuable massive sulfide copper and nickel ores, and also limits the system for detecting electrochemical effects in the ground due to sort of charge storage induced polarization effects. So one of the limitations is that we can't actually use B or E field sensors, which would be more sensitive at low frequency. Only DBDT sensors are operation. Those have a 1/F amplitude fall off, and so they have good high frequency sensitivity and poor low frequency sensitivity. Aircraft EM noise means that you always need long sensor tethers, and that complicates operations. So the need for a safe flight speed, you can't really safely hover helicopters for long, and economics means we have to have limited averaging times for noise reduction, critical at low frequencies, and existing systems are slightly expensive, but there's a lot of flying done. So I've mentioned that rotation noise is a problem. Tethered systems are complex pendulums. So this is just a sped up video of a system beneath a helicopter with this back and forward motion here, and there's a yoke point down there at the bottom. And so you get all these things rotation. This the receiver flies in something called a bird, and it just so happens that there's a real bird at the end of this picture. There's complications with these things. The period back and the pendulum period in line back and forward has got a different frequency from side to side due to changes in air pressure. But you can certainly see how the bird shell is rotating, and so our sensors inside rotate. Okay, so the next thing is most airborne sensors measure DBDT data. This spectral plot has got sort of spectral amplitude in volts as a function of frequency from 1/10 of a hertz up to 100,000 hertz. And this was using an induction magnetometers for magnetic fields, X, Y, and Z directions down here. And DBDT data at higher frequencies, so the cut even point was about 1 kilohertz, where their signals were about the same. Above 1 kilohertz DBDT, you could clearly see the spherics, the VLF stations. Below 1 kilohertz, the B field sensor showed up distant transmitter harmonics quite well. And I hope there's big amplitudes here from operator motion, from people walking around the sensor. And this was just data acquisition noise. So to get good low frequency data, we want B fields rather than DBDT. This is an example of some airborne data from a different EMinar project, where we measured B fields. That's 3 different components of B field in the top plot, and 3 of DBDT. So it's pretty much over the same bandwidth. The dBdt, this thick black band, is the VLF signal from a transmitter 2,500 kilometers away. The big spikes are spherics, which is lightning strikes, which is our AMT sources. These double patterned things as the transmitter waveform, and you can see the transmitter waveform on the B field as well. But this B field has this gradual motion up and down, low frequency, and that's actually tied into rotation. So these are measured rotations in the bottom, and you can see they've got pretty much the same frequency content. So to make decent B field measurements, we need to be able somehow to correct for rotations. So to do that correction in terms of coupling, if we had a 50 femtotesla sensitivity of our sensor, in the Earth field, let's say 50,000 nanoteslas, that requires a pointing accuracy of 1 part in 10 to the 9. If our vector sensor is sine rather than cosine coupled. That's equivalent to an angular resolution of 1 millimeter at a distance of 1,000 kilometers. So that's just incredible accuracy required, which is why most rotation sensors just can't provide the rotations we need in terms of B field. dBdt sensors are a bit better because they've got less sensitivity, but they're less sensitive also to the signals we want to see. People have tried to address this. This is Ben Pelzer and sort of Gordon West, Peter Hurley, and others worked on a air hockey style suspension system with this sort of massive assembly with sort of compressed air providing sort of a bearing so that the central region where your receiver is, your sensor is, doesn't rotate. But this whole thing weighs close to a couple of tons and is hugely sort of difficult to lift off. There are some alternatives to try to get around rotation noise. You can use a total field magnetometer. And HeliSAM by Gap Geophysics has, they have flown, they collect low frequency data from a ground transmitter. Here it's shown with the helicopter, but they have flown using a sort of drone come UAS as a tow vehicle. So total field measurements using optical pumping, they presently bandwidth limited to less than a couple of kilohertz, is not ideal for EM. The big problem is they only measure the component of the secondary field in the direction of the Earth field. So if this blue is the Earth field and you've got a secondary field perpendicular to it, it doesn't actually change the magnitude of the total field significantly. So what that means is if you're using a total field magnetometer, you measure the horizontal component in India, and you measure sort of subvertical magnetic fields in Australia or Canada. The other problem with optical pumping mags is they have much higher noise than induction magnetometers or SQUIDS, so you need more powerful transmitters. So the first sort of conclusion is that UAS wouldn't be a good replacement for airborne EM systems. Ground wire and loop sources are inefficient. Powerful, reliable helicopters for airborne EM transmitters are multi-billion-dollar devices. So there's no short-term incentive not to have a pilot on board. If we go for lightweight sensors suitable for UAS, they tend to have more motion noise than heavy ones. So all the low frequency sensors that are put on under UAS are much noisier than the ones in heavier suspended, in heavier sort of housings with suspension systems. We really want to get B field, and rotation noise is exacerbated in that. So the first sort of conclusion is there's no obvious benefit to unmanned systems to replace existing EM systems by sort of cutting out pilots. But I had to give things a bit more thought. And on the left, here's a plot of some sensors. If you have a sensor in a shielded room, this would be the noise levels you might measure, which is sub-picotesla per root hertz. When we operate that outside a shielded room on the ground, noise levels are higher because there's microseismic noise, there's ambient noise from all sorts of things. And if we operate those same sensor in the air with a suspension system, at 100 hertz, the airborne noise is half to 1 order of magnitude noise in a ground sensor. At 10 hertz, there's 1 to 2 orders of magnitude noisier, and at 1 hertz, 2 to 3 orders of magnitude noisier. So that's with very heavy suspension. So the obvious thing to me was really, if we want to get good data, we need low frequency, we need sensors on the ground. And a number of people have actually thought of doing this. There's an ExxonMobil upstream patent where they said you've got a whole batch of ground EM receivers and you fly a transmitter above that. They were suggesting the system would be useful for hydrocarbon exploration. And they were saying the big advantage was signal to noise reduction through having multiple sensors. Benkert and others with Vale developed a what they call the ground floor system. A, B, C, D, E, F, and G were ground sensors they put on the ground. Then they flew back and forward with a conventional VTEM system. And this colored data is the data collected at point G, 200 meters from the WD-16 target, which is quite a small target. So by sensors on the ground were certainly sensitive to targets off to the side. So we did some modeling. The other advantage of having ground sensors, if you put them down, you can also measure electric fields as well as magnetic. And simultaneous acquisition has signal to noise advantages. As long as your internal noise is low enough and your systems are sufficiently linear and the noise is correlated, you can do a big amount in sort of improving signal to noise. But modeling showed that by having sensors, here we had 25 stations on the ground in a 1 kilometer square survey area, spaced at 250 meters. So there's 5 of them, say, at the stop line. So each of these, this is what we measured by the sensor at the top left-hand corner if we flew an airborne transmitter. If we have a sensor here close to our target, shown white, in the white loop, we see a very big response. But even 500 meters, well, sort of 300 meters away, we would still get a clear response from other sensors on the ground. So the advantage of this is these sensors on the ground collect good low frequency data. They collect data for a lot longer time. You've got huge, you can do significant sort of averaging. So we predicted that for bigger EM targets of sort of economic interest could be easily detected with 500 meter space ground stations and 500 meter airborne transmitters. So how could UAS come into this? Well, Amazon has tested sort of delivery, and the Amazon technology is such that they're not going to just come and drop the package somewhere over the house that's meant to be delivered to. They're going to stick it on the front lawn, avoiding the toddler and the pram and the dog. So to handle the obstacle avoidance, find the best place to put things. So the question is, could this technology be used to stick out our systems? The advantage of this, we could collect both B and dBdt because you don't have the rotation noise, the system is fixed on the ground. We could potentially use tripod magnetic field sensors, which minimize wind noise compared to other systems, so not much worse than having buried sensors. How would we get E-field data? Well, ground contact possibly with high impedance electrodes, or we might have sort of what you think of sort of as taser implementation. The delivery vehicle could shoot an electrode into the ground along with a bottle of water, so you get there's a whole bunch of things. Why do you want E-fields? Well, they're sensitive to resistors as well as conductors, so you get much better geological mapping. So the system would get better data than airborne EM at lower frequencies. And it would get a high spatial density potentially that systems like AMT and AMT need but don't currently provide. So the EMinar P1204 conclusions were that UAS supported, we were calling them grasshopper arrays because the sensors would move in a swarm following the transmitter. They should be developed to operate with existing transmitters, sort of a hybrid system. It solves the existing issues of motion noise, aircraft noise, so we can get through deeper conductive cover. E-field permit detection of resistive as well as conductive targets, so we can collect AMT data when the system's not nearby. You get longer stacking times without loss of spatial resolution. There's no null couple targets. One of the problems with a fixed transmitter is it can null couple to a target. So we're a lot sort of better off in terms of finding targets at a variety of strike angles. But however, we're going to need inexpensive mass-produced sensors. And this would be something for big investment, which hopefully mining companies will bite the bullets and do. There are, of course, all sorts of challenges. Geophysically, if you take one ground node with an induction mag and cross T dipoles, you're looking at 30K plus. Realistically, that can shrink to less than 10K, I think, if it's mass produced. Electric dipole emplacement is an issue, particularly if it's not going to be human sort of porous pot planting. And there's going to be a lot of software development required for acquisition modeling. In terms of UAS developments, you're going to need cost-effective multi-UASs flying at low altitude beyond line of sight, which is the big problem at the moment. You need to be able to plant and retrieve receivers and sensors. If you've got a helicopter flying around, currently that's simply not permitted. So we need some method of absolute avoidance of a piloted helicopter carrying the transmitter. And so there's range and payload issues I won't get into. Okay, I mentioned the moon, where locating limited water and ice is of interest and geological mapping and sounding. So compared to Earth, the moon is electrically resistive. There's not much salt water around, so higher frequencies are needed. 5 and 20 megahertz systems see several kilometers down. The other big thing about the moon and Mars is they have solid cores, so there's no magnetic dynamo, very small ambient magnetic fields. So rotation noise is not an issue. So the issues we have on Earth with our airborne sensors will generally not be an issue on the moon or Mars. The next thing, in terms of electric field measurements, there's no Earth ionosphere electric field gradient. So potentially we can use non-contacting electrodes. We don't actually need ground contact. And such electrodes currently exist. They have noise levels of around a microvolt per meter in a Faraday cage. So I'll talk a bit about that in a moment. you'll need lightweight compact systems. So updated GPR and EM systems for the Moon and Mars are coming. There's funding out there for their development. I can't tell you about the sort of 2 projects I'm involved with because they under sort of government embargoes, waiting announcements. I was hoping I could, but it's they were meant to be announced in May, but they haven't been announced yet. Okay, so back to a previous EMinar project, we were trying to develop airborne electric field sensors. And we were looking at measuring the potential between a couple of sheets, but actually measuring the charge moving between the sheets rather than the potential on them. And part of this was attempting to determine the optimum area and separation of sensor plates. So the voltage difference is the electric field times the distance between them. The charge is Q upon V. When you work out the charge induced on the plates, is actually nothing to do with the separation D between them. It's just given by epsilon, the area of the plates times the local electric field. So we built and tested sort of systems with 2 copper sheets, an insulator between them, and electronics to measure, to work out how much charge we have to shift between them to keep them at the same potential. So this was sort of one such system. We had conductive sheets in a plastic case, internal electronics. We had charge amplifier, voltage amplifier to keep them things at constant potential. We had an FM transmitter, so this whole thing just broadcasted results. We couldn't afford to have any grounded wires touching it. And this was very good in a Faraday cage. But as soon as you took it out in the air, it was absolutely useless. There was just too much noise due to charge on windblown dust. There's just a huge amount of that moving around. There's the Earth ionosphere gradient, sort of 100 volts per meter, which varies between -100 and +300. And however, this, which proved totally was successful in a Faraday cage, but useless out in the open, could very well be something that works on the Moon to measure electric fields in flight at quite low frequencies. So getting back to the title, low noise, lightweight sensors for cheap UAS rather than Amazon style delivery. One of the options could be to use total field sensors because they eliminate rotation noise, which eliminates suspension systems. 3-component vector sensors could also potentially work if you can add them up vectorially to get total fields. However, there's quite a lot of defense-funded research looking at things like light shift dispersed optical mags, which theoretically you can build on a single chip with maybe 20 femtotesla per root hertz total field sensitivity and vector sensitivity and bandwidths up to VLF. There's a variety of other quantum devices under investigation. Why quantum? The standard quantum limit for an atom defines sort of the maximum sensitivity, but this limit is sort of reaches 1 femtotesla per root hertz for vapor volumes, for warm vapor less than a cubic centimeter. And so there's quite a few lab devices now which are achieving tens of femtotesla per root hertz sensitivity that they're looking at using laser integration and moving onto sort of chips. So they're looking at, these have got going to be quite miniature compared to the induction coils we used to. So I've just slapped together a few things. Noise. This is noise in Teslas per root hertz or nanoteslas per root hertz. Up here are the small commercial magnetic sensors using things like magnetoelectric effects, giant magnetoresistance Hall effects. They're all way too noisy to be useful. This red is one of particular induction coil magnetometer weighing 500 grams. These are the optical pumping typical noise, which is much noisier than induction systems above a hertz. Fluxgates are sort of too noisy to be useful. This is squid noise in the field. But these new devices is shown sort of in black here, so they look potentially going to be better than our existing systems. So the question is, when will we see these? Well, the first thing is defense research has to be completed and successful. It's quite possible that that research will be unsuccessful, but then we'll only find out about it if investigators choose to publish. The other thing is these sensors will have restrictions on them, and defense is unlikely to make them freely available unless submarines stop being a threat, tunnel detection becomes unimportant, or other technology becomes better, and international traffic in arms regulations will probably be required to get them around, which limits usage of quite a few geophysical systems already. And the other possibility is some universities that I'm not aware of, not constrained by defense contracts, might commercialize that. So the other thing is that I'd also say that we currently have electric field sensors that will work on the moon. Okay, so what about MT, which is what the seminars, or the host of the seminars is all about? Chip size quantum vector sensors are theoretically on the way. They work in the lab. Better than 0.1 picotesla per root hertz, bandwidths suitable for what we want. So you can replace essentially your big clunky 15 kilogram sensor with a chip, and obviously it still needs batteries, etc. So you're looking at less than a kilogram rather than something huge. Currently, AMT would be feasible with lightweight induction sensors, but they would also be improved by these new ones. UAS is tricky planting electric field sensors that have to be quite a bit of work to get that working well, if at all. And regulations need to improve to permit beyond line of sight before we can really say UAV unmanned aircraft systems will be useful. So in summary, lightweight, low power transmitters are pretty much, they have very limited number of applications geophysically. So UAS is not going to, UAS can do those, but it's not much help to anything. Hybrid controlled sort systems may be feasible. So piloted airborne transmitters, array of ground stations with unmanned aircraft transport, that's as described in that public report. And natural and cultural source EM systems may be able to benefit from unmanned systems and small sensors in the long run. On Earth, sort of pretty well soon, I guess, rather now, the moon soon, and other planets in the future. So thanks for your attention.
Yeah, thanks very much, Jim. Absolutely wonderful. That really, for me, was very educational. There's a lot of thought in you, but you really brought it all home. So one quick question, perhaps. Have you thought about capacitive electrodes?
Capacitive electrodes have got strong frequency dependence. So essentially the ones I was describing is charge coupled electrodes. So they do capacitively couple to the environment. But we're counting charge needed to keep them at a constant potential rather than trying to measure the voltage as it fluctuates. So it turns out that has similar advantages to making a B rather than DBDT measurement.
Okay. Yeah, because I've looked at some work recently and the capacitive electrodes are pretty good down to about 30 hertz. So
Yeah.
I thought, you know, if you can think of a drone the same way that the ocean bottom people do with having their electrodes at the end of a 1 meter boom, maybe you could think of deploying capacitive electrodes the same way.
Yeah, the ones I've worked with are good. We certainly tested them at 1/10 of a hertz and they were good. We didn't try testing longer, but there's no reason they wouldn't go have a flat response to lower frequency.
Yeah, now I'd like to get questions from the audience, and Dennis Woods has jumped in. I'll read this out because it gets in the record then. Dennis says, I was going to call you out on a number of your claims that I take exception with, but after your slide showing my advertisement from a decade ago, all is forgiven. So comments, he says, comments. I guess, do you have any comments? I don't know quite what you're asking comments for, Dennis. Do you want to come live? No. Oh, he's actually, yeah, we've lost Dennis.
Yeah, it was one of the sponsors of that research was Abitibi Geophysics, who gave me a large number of their pads to use for future calculations.
Okay, is there any other questions for Jim? Dennis says, sure. Oh, sure. Yeah, he'd like to. Okay. Yeah.
Am I muted now?
You're live, Dennis.
I'm unmuted. Yeah, well, I never dreamed that that throwaway line would rise from the dead after almost a decade and show up on one of your presentations. I'm just absolutely amazed. Did you actually make those notes at a conference someplace, or did you take?
That breakthrough that the charge had nothing to do with distance was actually made on your notepad, which was sitting on which was the scrap paper on my desk. So it was post-conference.
Okay, well, fair enough. At least I got it. I would like to, I would call you out on one thing. You seem to give HeliSAM short drift here. Your claims that, you know, there's no airborne system that works well below 25 hertz, and you did show some slides of HeliSAM. You made some comments, but you know, I think it's got more to it than what you're giving it credit for.
Yes, it's, well, certainly as given the choice, you'd want vector rather than total field system, but its rotation sort of noise kills you. And certainly the induction magnetometers are much lower noise than the optical pumping ones at sort of at higher frequencies. So yes, you know, sort of at sort of sub 10 hertz, HeliSAM works quite well, but again requires a very high powered transmitter, higher powered than other sort of airborne systems. It's so yeah, it no doubt has its applications, but it's not. I don't think it will do as well in the future as things like that, as the ground arrays with overflights.
Okay.
Yeah, Ben Murphy's just thrown in a long question. When you were discussing the Amazon delivery approach to sensor development, I think you mentioned using the tripod induction coil approach for measuring vector B. And I believe you said that actually works quite well. I was surprised by that, as the few examples I've seen haven't looked that great. I was wondering if you could comment a bit more on the considerations involved in the tripod approach to get good results and how that might map to an Amazon delivery approach.
Sure, the tripods work well when they A, rigid, and B, small. So they sort of really good when when say the length of your sensors is less than 50, say 50 centimeters. And sort of they're in a rigid housing, and they sort of planted firmly. The other issue comes in as to how well can you correct rotation, and that's not a trivial matter. So if you don't have good derotation software to get things back, you introduce quite a bit of noise into things. So I've seen extremely good tripod data from Western Australia with small compact systems, and I've seen bad tripod data from other things. So I think there's a bit of an art to it. It also, if there is high wind, it does help to have a windshield, sort of like a plastic compost bin sitting on top of it, which could also be UAV delivered, that once the thing is planted, you just drop a cover over the whole thing. So that of course becomes tricky in rough topography, but out in the flat where wind is often the biggest issue, that make a tripod system with a windshield works very well.
Okay, thanks for that question, Ben. If there's no more questions from the audience, I'd like to thank Jim again for absolutely wonderful presentation. And I'll just quickly remind people who we have next week is our EMinar is on Juan Carlos Afonso at 1300 UT, whatever that is in your time zone. So on that, I'll say thanks again to Jim, and good night or good morning to everybody out there, and see you next week. Thanks, Jim. Bye for now.
Bye.